All right, thank you, Emil. So thanks everyone for joining, and Emil for the introductions and the organization of the training activities. Very valuable and very important. Yeah, my name is KIOS CoE, and I'm a research assistant professor at the University of Cyprus. And I have been working on the topic of emergency response and technologies, ICT technologies for emergency response for the last 10 years, and closely collaborating with first responders in Cyprus and in Europe, yeah, to develop tools that people can use to make their lives easier at the field and also save lives. So I'll give you a bit of background related to KIOS and research unit that me and my colleague Christos Kirkou that we'll talk later on are working in. And later on I'll overview a bit of the technologies that we have been developing in order for these tools, AI tools, to be able to be used in practice. So the center right now employs around 160 researchers. We are in the we are based in the university campus, which is in the Nicosia, the capital of Cyprus, Nicosia. And most of our researchers have a background in electrical engineering, computer science, physics, mathematics, civil engineering, and mechanical engineering. So we are most of us are engineers, and we like to solve problems, and the challenges faced by disaster management personnel are quite um, important, and we have been committed to working with them closely to deliver on these tools. So the broad scope of the center is around critical infrastructure systems. Critical infrastructure systems include the energy and power networks, the water supply networks, the transportation networks, and the healthcare system. And on top of this, we are looking at issues like telecommunication, networking, and cybersecurity related to the critical infrastructure systems. And of course, disaster management and emergency response are the key topics that we are trying to solve in order to make these critical infrastructure systems more resilient to disasters. So we look at the broad scope of the prevention, preparedness, and response to disasters, especially in these large-scale systems. The group that works with the emergency response technologies has been very successful over the past years in attracting funding, especially from the EU, to develop the technologies that we are going to show you. And because of that, most of the technologies that we have been developing up to now, we are proud to give them out as free tools for people to experiment and use and test in practice. And as Emil said before, most of the results of our research and innovation, we give them out in the relevant project website. So especially with ARTION, we have and we strive to give out all the data we collect from the different exercises, the annotation of the data, to help out researchers develop new AI algorithms. And also our own AI algorithms are posted there for people to freely download and use. I'll give you more details on that, and my colleague Christos later on will give more details on the algorithms that we have been developing for supporting first responders in the field. So we have come up with this accumulated knowledge regarding the needs of first responders by closely participating in various different exercises, and and real missions, real response operations. For field exercises, we have been actively working with our colleagues from the Cyprus Civil Defense to collect data in different field exercises, international field exercises that take place in Cyprus. On the top left here, you can see all the one of the large annual exercises that we have in Cyprus for earthquakes. People from first responders from France, the UK, Israel, and many other countries come to Cyprus to jointly train and exercise. We have various different search and rescue exercises at sea, for example, this is a military, a non-combat military exercise related to the search and rescue and the safe arrival of refugees from the Middle East. We have participated in many small exercises that are coordinated by the Cyprus Civil Defense. And on the top right here, you see a few of the an instance of some of the exercises that we have been doing in Greece. We have also participated in exercises in Austria and in Italy and many other places across Europe. And on the bottom right, you see one instance of the training that we have been doing closely with the Cyprus Civil Defense in using drones for emergency response operations. And most of the data that I'll show you today are from sensors on board drones. But I would like to emphasize that it's obvious that first responders have the means now to collect a lot of information from the field. And the idea is how to structure this data in a way that can be processed and give you added valuable information regarding what is happening on the ground. So this is just some of the trainings and exercises that we have been doing over the last several years. We have also participated in real operations with the first responders to help out with different tools that we have been developing. On the left column, here you see a lot of different search and rescue operations for missing people that we have been doing either in urban areas on the bottom, coastal areas or mountainous areas here in Cyprus. Large events like football events and firefighting operations, especially during the June, July, August summer season in Cyprus during the night, where we had to operate with drones to find the hotspots and the risk of fires approaching locations where there were villages and accessibility to roads and so on. So you see how challenging these environments are. And later on, we'll show you how AI can be used in these very challenging environments to help out and gather information. And of course, drones here were very valuable because during the night, the manned aircraft couldn't operate, and so one of the very beneficial use cases of drones is for firefighting, is especially during the night hours where the information is very restricted. Another thing that we have been looking at and also operational right now in Cyprus is we have rolled out an open source telecom infrastructure based on a technology called LoRa. If you are not familiar with LoRa, it's similar to Wi-Fi, but longer range. So we have rolled out 12 base stations to cover a whole city. Here, the coastal city of Larnaca in Cyprus. And through these base stations, we collect a lot of different environmental sensor data, like weather data and smart meter data from different meters, like the water meters, the power and consumption from the electrical grid, and many other sensors that we placed in the field. So right now there are more than 1,000 sensors. We originally started with 300 sensors and 12 base stations, but we are continuously adding more sensors, and we have a project now with the municipality of Larnaca to even introduce 3,000 more sensors for different collecting different measurements. And I'm just emphasizing this to show that it has become very easy nowadays to collect valuable information for preventing, preparing, and responding to disasters. And this information, of course, cannot be analyzed in real time by human operators. The effort will be very big, and thus AI is a very nice tool, a very important tool to be able to scale up to the analysis that needs to be made when all this digitization is happening across cities and countries in the world. So I'll give you some of the examples here. Let me mute it first so that we don't, the sound doesn't need to be done. Some of the examples that we have integrated and provided a full operational tool for different uses. This is a drone tool that takes a commercial drone and converts it into a monitor inspection agent. So the drone is instructed using machine learning tools that are running on the computer here on the top to detect, track, and assess the risk of fires from the power infrastructure. So the drone flies across the the medium voltage and the high voltage power lines. The plan is to run this every year from January until April, and to inspect the whole infrastructure during this period. The medium voltage lines in Cyprus total about 1,500 kilometers. And using this technology, we are able to monitor it on time and detect if there are any branches of trees that need to be cleaned in order to minimize the risk of fire happening during the summer season. So this is a very novel, let's say, preparedness tool and prevention and preparedness tool. Prevention because we minimize the risk of fires happening, and preparedness because as the drone flies across all these areas, we collect a lot of gigabytes of data, and we have an up-to-date 3D model of all the areas that the drone has flown, so that people know exactly if there is an emergency and they need to go back and see the field where the emergency is happening to see the most updated data regarding that area. Of course, as you can imagine, we collect a very big volume of information when these missions are happening. We on the drone, we have a number of different cameras that collect a lot of gigabytes of data, but also we have a solid state weather station on top, and so on. And all this data is collected, as I said, across the whole of Cyprus once every year during the first 3-month period of the year. And that will make it very challenging in analyzing that data and finding a lot of valuable information. And of course, all these tools run on them algorithms that are doing object detection, that are doing trajectory planning to avoid obstacles while the drone is flying, and so on. Another tool that is used for, let's say, response operations, again with a drone, similar as before, we have incorporated algorithms to make a drone autonomous, and in this case relates to search and rescue at sea. So the drone detects, in this case, boats and people floating after an accident, and then tracks them until the marine police arrives to give some help. So the whole operation here, as you will see, is done autonomously, and the people that operate the drone need a very little technical experience on how to use this tool that we have developed, and also this tool works with commercial drones, so there is no need for specialized equipment and so on. It's simply a mobile application that processes information data from the cameras of the drone and the telemetry of the drone, and takes decisions by itself. So in this case, you see here, we want to track this boat, and I'll skip through a bit of this. I think you get the picture. It detects and tracks the boat. It tries always to bring it at the center of the image. And when it detects people, let's say, that are at sea, it also monitors the location of those people and gives the coordinates back to the command and control center in order for the search and rescue mission to be successful. Some more advanced tools that we have been developing through different European projects. I'll go in this. I'll show you here. One of the tools that we have been developing relates to a swarm of drones and how you can easily coordinate the action of a swarm of drones to do different tasks using only one operator. And here, this is a web-based platform where it detects all the drones that have been connected on the same Wi-Fi network, and shows the location of the drones, the live stream of the camera, and then you can put very simple click and go missions that are predefined in order to help out the first responders have a clear situational awareness of what is happening on the ground. So in this case, for example, the drones are building a mosaic of the area in real time. So the operator just clicks where the drone should go, and then the drone autonomously navigates across the area in order to collect data, and that data is shown on the map in real time, so that people in the end have a real-time map reconstructed of the vicinity where the emergencies happen. On this tool, we have added many new features like stitching the images and doing a 2D or a 3D reconstruction. We have also introduced object detections, as I will show you later on. So as the drones are searching the area and doing a situational, doing a map, they also pinpoint location of very important objects of interest. And the algorithms are scalable to any kind of load. So here you see, for example, the extreme scenario where there are a lot of objects of interest that need to be monitored, detected, tracked, and monitored. For example, here, in addition to where the objects are, we show and the trajectory of the objects, we show the speed of the object and the path that it followed. The 3D reconstruction is done offline, but the operator can still use the platform that I showed before, and when the reconstruction is ready, it's shown on the map. So we have done that for many different cases in Cyprus, and we provide this data publicly available for different forest fires that happened, especially in the 2021, the summer period of last year. There were a lot of fires happening in Cyprus, and for all of them, we went and collected data and created all these very detailed maps for recovery missions for first responders to take action on how to safely restore the area that was burned. Also, in the reconstruction, we use state-of-the-art LiDAR sensors, as I'll show you later on, and you can build point clouds. So this is a very detailed point cloud of the university campus where the KIOS is. And as you zoom in, more points are loaded. This is around 5 million points, 3D points that show detailed levels of the elevation and the structure and the texture of the area at hand. And this can be done in real time as well. So as the drones fly to collect data, you can reconstruct in 3D the environment, which is one of the things that are very useful for situational awareness. And on top of this 3D model, you can start introducing object detection and navigation and so on. Yeah, so the center has a lot of different hardware, commercial hardware. We focus a lot of commercial hardware so that all the technologies we develop can be applied and are practical in the field. So most of this technology already is being used by first responders, and the idea is to introduce in this technology intelligence, and intelligence using software that can process the data using machine learning algorithms in order to provide informed decisions for first responders. So we do all these data analytics offline in our data centers, as you see here in the picture in the middle, and then the result of these algorithms we implement it on the operational hardware so that it can be used in real time. As Emil mentioned before, one of the things that we have done within ARTION is to develop a custom-made application to collect data not just from drones and sensors that I mentioned before, but also from the mobile applications that first responders most of the time carry with them in the field. So the idea here is to enable first responders to use their smartphone and collecting valuable information that are needed during an emergency. Of course, the standard stuff that is collected is location information, the speed that people are traveling, and if they are standing up or they have fallen down, the trajectory that they followed, especially during search and rescue. You need to see if there are any spots that have not been searched adequately and so on. So we have developed this application that collects all the sensor measurements from a smartphone and then stores them in a database. And then the idea is that we give it out to the research community to develop new innovative algorithms using that data that can be collected from sensors on the phone. Also, I wanted to mention that another type of emergency that we have not investigated a lot, but in the past, but we have been asked by the Republic of Cyprus to contribute due to our experience over the last couple of years is of course the pandemic. And KIOS has developed all the ICT infrastructure for collecting and analyzing information related to the spread of the pandemic in Cyprus. So during the last 2 years, we have been very busy in developing all the ICT infrastructure for sampling and contact tracing and the recoveries of positive cases in Cyprus. And this process has given us a very nice opportunity to also demonstrate the applicability of AI algorithms, because during this time we have developed algorithms that predict the spread of the virus when the government takes different measures. And this was very well received by the medical community that takes decisions and gives consultation to the government on how to progress with the restrictive measures. And I think they were very successful in doing so, because we had all this information and the analysis of information from the data we collected. So the message I wanted to pass is that in many different emergencies, first responders are able to collect a lot of different data, either from many different technologies, mobile apps, as I mentioned before, drones, which is a hot topic, or traditional ICT systems. And is becoming very easy to access all this technology right now by first responders. And the aim is to capitalize on the data we collect from all this technology and give valuable information back to the first responders. So from our research we did during the discussions we had with first responders, I'll give you a summary of all the important information that need to be extracted from data that we collect. For example, in the case of fires, in very important parameters include the height of the fire, the surface area of the event, the color of the fire, the temperature of the fire, the spread rate, the vegetation type ahead of the fire, of course, weather conditions, and the whereabouts of citizens, buildings, accessibility of roads, the teams and means. So this is very important information that with current AI technology and the right data collected from the scene, it can be extracted. This information can be extracted very easily, as we are trying to advocate here, and as we will show later on in the next presentation as well. Other examples focusing on flooding scenarios that we have been witnessing over the past several weeks and months across Europe. Important information that needs to be taken into account include the height of the water, the area that has been flooded, of course, then the rainfall intensity, the water speed that the water is moving across the area, weather forecast, and the way that water could be discharged. So the critical infrastructure that is in place where it can be engaged to discharge all this water. And of course, the location of citizens, buildings, roads, teams and means, industrial and sensitive areas, the topography, the 3D elevation is very important, and the hydrographic network. With regards to earthquakes, as before, the important information includes the risks of damages from the prediction of damages of the infrastructure, the weather forecast, the estimated population that has been affected, the whereabouts of citizens, buildings, roads, and teams and means. So the main aim of the next few slides is to show you how all this information can be extracted from different sensor measurements, data that has been collected. I'll give you some examples here of the sensors that can be attached and be accessible by first responders using drones. That is a very hot topic right in these days. So we have on the drones, for example, cameras, RGB cameras, thermal cameras, and multispectral cameras that get frequencies bands across various areas of the spectrum. Then radiometry, LiDAR sensors, CBRN sensors, and so on. So all this information, when processed in the right way, and when trained on how to extract information, they give very valuable insights on all this information that need to be extracted by during the incident and by first responders. So I'll give you the 3 examples that I mentioned before. I'll give you a couple of insights on how this can be done. For example, for fire analysis, that is very important during the spread of the start and the spread of the fire. Information related to weather, local weather is very important. So, for example, there are in the market solid state weather stations that can be attached to drones and collect information from the local area that the emergency is happening. Topology can be extracted very easily with now common LiDAR sensors that just measure the elevation using the transmitted light waves. Then the fuel conditions and the fuel type can be extracted quite easily using multispectral cameras that just do simple mathematical functions to understand if the fuel is either dry or it's hydrated vegetation or it's rocky area and so on. And then using models, I'll show you an example of a model here where using all this data as input and standard fire modeling simulators, people can understand where the fire will propagate and how long it will take to propagate in those locations, and take preventive actions to minimize the risk of the fire spreading. With regards to the floods that I mentioned before, there are the important parameters, of course, again, are the topology, the drainage, the soil type, and the rainfall, all of which can also be collected using the same type of sensors. So the rainfall using the rainfall intensity can be extracted from either cameras and the weather sensors, the soil type, again, using multispectral cameras, then drainage and the topology using LiDARs. And then all this information can be input into simulators that can model the propagation of the flood and how to further collect new information to safely and accurately monitor the evolution of the flood. And then again, as a last example, the earthquake assessment information, and this can be done as a preventive action, is to assess the risk of damage to buildings, let's say, and take preventive measures to minimize this risk. And information needed for all this type of risk assessment include soil type, building quality, the distance from the fault, the number of floors of the building, the population density in that building, and the distance from publicly open areas. And for some reason, I cannot play this video. But all this, most of this information is static information that can be collected offline. And the soil type, again, using these sensors that I mentioned before, like multispectral sensors and machine learning tools to detect and store all the additional information that are not available offline, like the number of floors and the structure of the building and so on, and the building quality. And then there are very accurate and open source tools like OpenQuake that take this information as open source, and they give you accurate risk assessment related to the damage from certain scenarios, what if scenarios. So for all these 3 cases, we have been in the process of developing these simple scripts where people can input their data, and get a different what-if scenario analysis based on the information that has been inputted. And we will populate the ARTION website with these scripts to automate the process of inputting information to these simulators and analyzing the data. And finally, with regards to the pandemic, as I mentioned before, I'm not going to go into the details here, but with all the information that we collected using ICT tools, so the number of tests that have been made, the number of positive cases, and so on, and the measures and the intensity of the measures, like the lockdowns or the restrictions of vaccinated and not vaccinated people and so on, we were able to train a machine learning algorithm to predict, as you see here, very accurately the evolution of the pandemic in Cyprus using this information. So we have been giving these tools to the medical emergency response community that has been taking informed decisions related to how to take less or more restrictive measures in the future in order to ensure the safety and accessibility of the citizens inside. Yeah, so we have during the ARTION project, we have been trying to test all these technologies that we have developed with first responders in the field, as Emil mentioned before, and we have followed and we are trying to follow a standardized process that the CBK, our partners, have been developing through their own experience and project development. And the idea here is to use and introduce this new technology in the exercises that will happen through ARTION in order to make a structured assessment on how this technology can actually, and the degree that this technology can actually help out first responders in practice. So it's not just developing and showing off the systems, but also assessing the degree that this has been successful in practice. So in this structured process that I'm sure Emil will detail the steps later on, we address key questions and key challenges and how this technology can help out to solve this key question in practice. And we have structured these scenarios in a way that these key questions are introduced in the scenarios, and then by using a specific technology, what was the benefit and the impact of the technology, especially AI technology, in these test scenarios. So I would like to finish here by saying that in summary, we as KIOS, we have been trying to introduce new systems that are user-friendly and solve real problems using AI technology. And we are trying to provide all this technology readily available for people to test and use in their own countries and exercises. We have been actively doing a lot of trainings, especially through the Union Civil Protection Mechanism training courses, and of course through the knowledge network here that funds this ARTION project to engage the community, and not just the scientific community and the first responders and the emergency response community, but also stakeholders related to hardware manufacturing and software development and so on, to show them the challenges, show them the potential solutions that can be done with this technology, and then try to also steer them towards developing new solutions for the emergency response community. And of course, field exercising and testing the technology in order to make sure that it meets the requirements of first responders. It also helps them out solve real problems in their missions. I will also conclude with the link to the AI portal if you need to access the material, either the videos or the data sets from the exercises or the algorithms that we have been populating there and the tools, ICT tools that we have been developing. And feel free to contact us if you need further information. Thanks a lot.
Okay, great. So let's begin. Hello, everyone. Thanks for attending this training workshop. My name is Christos Kirkou. I am a research lecturer here at KIOS, a Research and Innovation Center of Excellence, which is part of the University of Cyprus. My area of expertise is on computer vision and machine learning with application in real-time systems. And some of the things that we have been doing in the past few years concern applications in emergency management and response. So in this talk, what I will try to convey is what is AI? When we talk about AI, what exactly do we mean? What are some subfields and how are these actually used in emergency management? So let's start first. What is artificial intelligence? When we say we talk about artificial intelligence, so this is a buzzword that we hear a lot today across different areas, and it's important to understand exactly what is meant when we say artificial intelligence. So in general, we start with the word intelligence. It's the ability to learn and understand and make judgments or have opinions that are based on some sort of reasoning, according to Cambridge Dictionary. In the domain we're talking about is essentially the ability to acquire and apply knowledge and skills. And artificial intelligence is essentially trying to make computers acquire some sort of knowledge and then apply that knowledge into the real world to solve problems. It's essentially automating the behavior of an intelligent system. Now, this is, of course, a large branch of different sub-areas, some of which we have also mentioned today, like machine learning, for example. Some other sub-areas are computer vision, robotics, planning, natural language processing, and so on. So all these fall under the general term that we call artificial intelligence. And the goal of each of these subjects is to make computers smarter. In a sense, try to make them act a bit more intelligent like humans. And today, a very popular paradigm to achieve this is based on machine learning, which, as I've shown in the previous slide, is one of the sub-areas of artificial intelligence. And the major difference to machine learning as to how we program computers in a classical sense is that in the classical programming, we have data and we write code that is the algorithm that essentially processes those data, and we get an output. Now, there is a large class of problems for which writing explicit code may work for some instances of our data, but not for all. So, and the problem is we cannot actually express in explicit code a general way to solve a particular problem. So think of face detection, for instance. You cannot write a code that will recognize and detect faces for all faces in an explicit manner. So for those types of problems, the branch of machine learning has emerged where we essentially show the computer, or we program the computer to get as input the data and what type of output we want, and through some mathematical formulation, essentially tune some parameters to make this association. In essence, what the computer does, it's write the algorithm itself. And today, machine learning is used for a wide range of applications, from internet and the cloud. For example, when you do search on Google Images, it might use some form of machine learning to do the matching. In biology, to detect cancer cells, from media and entertainment to automated video captioning. In security and surveillance, autonomous machines like autonomous vehicles to detect lanes and pedestrians, and so on. Now, when we talk about machine learning, in itself is a rather large area. It has different types and different algorithms, but I think it's important to try and understand how each of these subfields is what it does and how it can help. So this describes basically the level of annotation we have for our data, the level of information, and what types of actions the machine learning algorithm has to take. So we have a supervised learning paradigm, in which case we can classify our data into different classes or do some sort of prediction, predict a real value for it, for example. Now, in these types of problems, we usually have data, for example, some sort of text, and we need to also provide the target variable or target class that is associated with that data. So we have some text. We can have, for example, the whether it's malicious or aggressive or not, some type of classification. The next learning paradigm is that of unsupervised learning, where we just have a bunch of data, and it's up to the algorithm to build this association and learn which data are linked together or have some sort of commonalities, and which are not, can belong to different clusters, for example. And this can be an instance of when we want to do anomaly detection. We want to discriminate between data that look normal and data that look abnormal. And the third and final learning paradigm is that of reinforcement learning, where we want to train an agent to act within an environment. Now, if we look at these learning paradigms in a bit more detail, it's basically we need to provide, for the supervised learning case, we need to provide some labels. So if we have images of fruits, we can say that this is apple, this is bananas. And the idea is we train this algorithm to reproduce this behavior from our trained data. And we test that same algorithm on unseen data, and we evaluate its performance on this unknown data, and we can say whether or not it performs well enough, or we need to do some additions. Then we go back, we change the way we train the algorithm, maybe we add more data, and we reevaluate again. Now, in the case of the unsupervised learning, we have the data, but we don't have any labels for the data. So it's up to the algorithm to build an association on which data types belong together and which do not. So this is a form, for example, of clustering. So we have some, we may have some, I don't know, some images of incidents, but we don't have any labels. So this could be crowdsourced images, and we want the algorithm to group things together that look similar. So this could be images of fire or collapsed building, etc. And last, we have the reinforcement learning paradigm. For example, we could train an agent to roam an indoor area and avoid any obstacles so that we can get images from that area when there is a disaster. So in this case, what we need to do is to build an environment. So this can be a digital, usually it's a digital software where the agent can maneuver within, and it performs different, it's free to perform different actions, and each action gives it a reward. Now, based on that reward, it learns how to do the action better. So over time, it gets better at doing the particular task. And all these algorithms have been used, if you look at the literature, have been used for different types of systems across different types of disasters. So they have been used in earthquakes, wildfires, floods, tsunamis, etc. And it's important here to understand why does it make sense to have all these disasters under the same umbrella, and talk about AI systems that can be used in emergency management rather than AI system for fire or AI system for floods. And it's because if we look at them all together, they have very many common characteristics. So they require modeling aspects, modeling of cascading effects from their impact on, for example, on critical infrastructures like power systems. They require having constant situational awareness, so recognizing what's the state of buildings, where the people are, etc. So developing an AI solution that can tackle one aspect in one disaster domain could potentially be transferred to another one. So it makes sense to look at these disasters together and identify the common problems that can be solved with AI. And this can be summarized, not exclusively, but some types of systems that AI and machine learning can help us build are systems that forecast events. So, for example, forecasting of earthquakes or flood, decision support systems that help experts make more informed decisions by accurately giving us a better situational awareness, decision-making systems that maybe autonomously deciding whether or not to route some evacuation vehicles, for example. And of course, this can also be built into automated robotic systems that can survey areas themselves, identify potential threats, and respond back to the command and control center. Now, to get an idea, here are some possible examples of AI in disaster management. So we could have fire detection systems that works over a video surveillance systems to build an early warning application. We can deploy drones with cameras in search and rescue operations and use AI to detect and track objects like humans, animals, and cars. So it would give us a better understanding of the situation. We can use AI to predict the evolution of a disaster. So how the fire will develop, how an oil spill in the sea will develop, and so on. It can also be used to identify potential threats when regards to evaluating the building structure early on, so we can eliminate the risk of collapse. We can use it to monitor in real-time traffic data and implement better evacuation plans in case of a disaster. And beyond what types of AI systems we can build, it's also important to understand that it can help different teams within the emergency management landscape. So as I mentioned, the fire detection system can help first-line responders like firefighters to predict how the fire will unveil, and so they can act in a safe manner. Rescue teams can be helped by search and rescue robots. Officers can have a better understanding of what is going on when machine learning can inform them in real time of different developments. and also administrative authorities can help in preventing disasters by using the forecasting capabilities that AI systems can provide. And another thing to keep in mind is that when we talk about AI in emergency management, it can be used across different phases of the emergency management landscape, but also across different spatial dimensions. So we have pre-disaster events that AI can help us in forecasting and prediction. It can help in preparedness when we're building early warning and vulnerability assessment systems. Of course, it can help in response by planning for cascading effects once the disaster has struck. And of course, in the recovery phase, it can help us in terms of mapping out what areas have been affected and what is the type of damage. And this can happen across different spatial resolution. So it could be at the building level, it could be at a larger area, and so on. So we have different ways of using machine learning to help us across all the disaster management phases. But it makes sense to understand why do we have today all this hype about machine learning and AI. It's basically been a perfect storm of different things happening in parallel. So we have first we have an increasing computational capacity and storage. This allowed us to process more data and explore techniques that are on the larger scale of data use. So using more data allows us to have better algorithms. And better algorithms mean they can generalize better by using more data. So they are more reliable to use in the field. And today, AI algorithms are used on a wide range of situations like perception, prediction, planning, etc. And the important thing here is this increased computational capacity has allowed us to use them in an automated way, because humans are very good at certain tasks, but the problem is fatigue, is looking at larger amounts of data. This is where AI can augment and help human experts. Now, the second thing that happened that allows us to use these algorithms in a much higher capacity is the availability of data. As Panagiotis mentioned in his talk, the first responders have a lot of diverse and data sources that they can use, from drones with multiple sensors to wearable sensors to building sensors and so on. And through the effort of a lot of researchers getting the data and also annotating them so that they can be used practically by machine learning algorithms has made it possible to increase their usability by the community. And of course, an important aspect here is that the data should not be underestimated. So the quality as well as the quantity of data has to be sufficient to train an algorithm that can be used and be trusted by experts in the field. And of course, the challenge here is that the rare occurrence of such events, especially in emergency response, makes it a bit more challenging to gather data. But for this, there are a lot of approaches like simulators or digital twins that are being developed to help ease the data availability problem. And here you can see an example of some types of data that could be used with machine learning. So if we have some historical data of, for example, what happened across different disasters, we can use that to train a planning algorithm. If we have weather information, we can predict whether it's a good idea to deploy one type of technology against the other, depending on the weather conditions. Through satellite data and remote capture data, we can do some analysis of imaging to find out areas of changing of areas and the situation in each area. We have crowdsourced data from mobile phones, which can be collected anonymously, and of course, social media data, which are another source of information. And of course, last but not least, we had a development in terms of AI algorithms, which have found themselves into robot devices like UAVs and drones, which together provide a very useful tool for emergency management. So they can be, for example, UAVs can be deployed in dangerous environments without putting human operators at risk, and they can help manage crew, the personnel, by analyzing themselves autonomously the information and improving the probability of success of a mission. And for the next few slides, I will focus a bit on UAVs as a tool for emergency management applications. So in the work that we do, we view UAVs as an embedded vision system. So it has a processing unit, it has a camera, and our goal is to use the onboard processing capabilities to do some image analysis and detect objects and understand the scene that the camera is viewing. And for this, we use computer vision technologies, which is in itself a subfield of AI and with a lot of interaction with machine learning. And the idea here is that we want to make computers understand what they're looking at in a digital image or video. And for this, usually we have different tasks that we can perform. So as you can see on the image, on the left, we have image classification. In this task, the output of a computer vision algorithm is usually a label. So in this case, it could be a chair. Or you could also draw a bounding box to localize that particular object in the image. You can detect multiple objects. So draw a bounding box across all the objects that you are interested in. Or even more, in a more advanced setting, you can highlight the pixel. So the individual picture element in the image that belongs to a particular object. So all these types of algorithms can be used in emergency management to analyze an image accordingly. So for instance, we can do an analysis of images captured from a satellite or drone to understand what is happening in the area, whether we have buildings or grass, and this can or trees or river, etc. And this can give us, especially in unknown areas, a better understanding of the surrounding. Or we can have a drone autonomously navigate an area and alert us if any potential disasters that it sees. And through using georeferencing technologies, we can view that on a map and accordingly plan what resources to send in each area. And in this space, we also did some work where we developed a data set for recognizing different types of disasters in aerial imaging, where we collected at the time a large data set of images capable of detecting collapsed buildings, fire, flood, traffic incidents, and we used that to do real-time processing on a UAV. And on top of that, we also analyzed the behavior of the systems in terms of what it actually uses from the image to come to a conclusion. So this is an important aspect when we want to have what is called explainable AI or more trustworthy AI. We need to, beyond the label that the system uses, we also want to understand why it gives us that particular label. So we ask the system to tell us which part of the image influences decision. So in the case of fire, you can see clearly that it's the fire area. In the case of the collapsed building, it's the area that has the demolished side of the building. So we can gain more confidence into these types of systems. And we have used this system on both an embedded setting using the onboard processing unit on a drone. And also we are developing Android applications that do this on the tablet by communicating directly with the UAV. Another type of system we're looking at is for object detection from UAV images, where we want to detect some objects, so for example, cars or pedestrians, and we can also want to track them. So as you can see on the bottom right, this system that is able to detect pedestrians, even on images that are of low quality, so there's a lot of noise in the image, maybe because of the data transfer or synchronization. And of course, the camera is wobbly, but again, we're able to detect people. So these are some things that we are also working on. And on top of this, once we have this information, we can start building more advanced systems, but at the same time also gather the information to be visualized in an appropriate platform. So we can start building tracking of people or objects, start classifying whether or not people are moving or are lying down, which can influence the decision and the different tasks that then the AI, the emergency personnel can take. We can also save all this data for future reference and plot trajectories of people, locations of person, directions, and so on. All this can be gathered in real time and visualized in an appropriate command and control center. So here we see an example of detecting multiple objects. We can identify the types of objects, the types of their velocity, the direction they're going, and we can select them to track one particular object or not. Here, this is a search and rescue operation where we are tracking people at very high altitude, so much higher than what we have in the previous video. And this changes dramatically the way that we built the AI system, so it has to adapt to this change of resolution, which is another aspect that is important to consider here. And as you can see, and I hope you can appreciate, it's not so easy for a human to first detect the presence of people, but also keep tracking them through the video. So the development of AI systems is very helpful in this case. So some other things we are working on are on the semantic segmentation, where we want to label every pixel in the image as to what type of class it is. And this is important. We want to identify roads, for example, or the state of a building, and we want to especially compare with previous time instances. So in this example, we trained a model to do road segmentation, to follow cars or identify evacuation routes. And as you can see here, it manages to identify the areas where vehicles might move. And using, again, the same methods, what we can do is to also do some post-damage event assessment. So we can have the same images captured at different time instances, and by comparing them, we can assess whether or not the building is damaged or the state of the damage. So this is also helpful in understanding what type of help we have to send in each area. So in my talk, I hope you have identified a few applications of AI. You appreciate that the AI and machine learning have a role to play in emergency response and can be used to build very useful tools to mitigate the risks and damages occurred by disasters. Of course, having said that, AI and machine learning are at the moment not at the level of fully automated deployment, but human expertise is necessary, and some parts of analytical modeling are indeed needed for a lot of things that we cannot do with machine learning, especially when we have limited data. And of course, an important aspect to consider is how these systems cooperate and interact with human operators in a way that makes the whole operation much more efficient. So these are just some food for thought, and thank you for your time and your attention.
Yes, I can see question. One of the weaknesses that ARTION app and platform has was the internet. We couldn't see the position of the responders on the map simply because their mobiles had no signal. Question is, can LoRa supply the disaster area with Wi-Fi? Can LoRa be remote? Can, for example, the sensors be installed on cars? And the last one, what is the cost to cover, let's say, 10 square kilometers?
Yes, thank you, Emil and Marino, for the question. Indeed, always the connectivity is quite challenging for especially when operating in rural areas. There are many different options actually. LoRa is one of them that is currently being rolled out in many different countries and cities. But LoRa is very low bandwidth, so I don't think LoRa will be the solution in that case. The alternative is satellite communications, which is much more expensive though. So there is a trade-off here. So it really depends on many different things. There is not a clear-cut solution for this. Yeah, we can discuss it. I mean, yeah, we have to see, depending on the scenario and the incident, which is the best alternative underlying telecommunication technology to use.